So we've reached a pivotal point in your organic journey, the point where we start to really have enough foundation of pieces of the organic puzzle to put together what organic is really about. So the first commandment I gave you was learn the functional groups. One of the tough topics we talked about previously, resonance. One of the most recent topics we covered, NMR spectroscopy. We've covered stereochemistry. We've covered intermolecular forces, a little bit. We've covered lots of things. And now we've covered enough stuff that we can talk about real organic stuff. Sure, all the other stuff is real organic stuff, but really the foundation of organic is about functional groups and their families. I've said that previously. Our book is organized into these 4 functional group families. And every functional group that falls under a certain family participates in similar reactions. So these are alkenes, alkynes, and dienes. That's 2 alkenes in there. Those kinds of things do certain types of reactions that are different from things that these do. These are sp3 carbons with electronegative elements attached to them. It's hard to categorize that whole thing without telling you specifics, but they're different from alkenes and alkynes. They react differently from alkenes and alkynes. This is carbonyl stuff. Aldehydes, ketones, carboxylic acids, acid chlorides, anhydrides, esters, amides, lots of things. This stuff we will spend a long time on in second semester organic, and this is aromatic compounds, again, second semester organic. We're going to cover these 2 parts of these 2 this semester, and we're starting off with number 1. Number 1 is stuff that has pi bonds, alkenes and alkynes. Number 1, group 1, family 1, are all unsaturated compounds. Unsaturated means you have fewer hydrogens than an alkane formula would predict. So an alkane formula says you should have 2n plus 2 hydrogens, where n is equal to the number of carbons. So 2 times the number of carbons plus 2 should tell you how many hydrogens you have in an alkane. And if you have fewer hydrogens than that, you're said to be unsaturated. So examples of unsaturated things are things that have pi bonds, but as it turns out, things that are enclosed in rings also have a degree of unsaturation. So there's a formula that says this is the number of degrees of unsaturation in a compound. Note, X means halogen, and there is not an oxygen in the formula for this thing. So something C7H14, 2 times 7 plus 2 plus no hydrogens, no nitrogens, minus 14 hydrogens, no halogens, divided by 2, we get degrees of unsaturation. Do the math. I'm waiting. 1. 1 degree of unsaturation. What that tells me is this compound either has 1 pi bond in it or has 1 ring. So something like this could fit that formula. Something like that could fit that formula. Or something like this. 1, 2, 3, 4, 5, 6. That could fit that formula. There's lots of options, but the number of degrees of unsaturation tells me how many rings and or pi bonds. Let's do one more. So something like C6H6, 2 times the number of carbons, plus 2, plus nitrogen, ain't got none, minus hydrogen, plus halogen, don't have any, over 2. That makes a du of 4. So 4 could mean it has 4 pi bonds, or 4 rings, or any combination thereof. You're probably not going to have 4 rings when you have 6 carbons, but benzene actually has a degrees of unsaturation of 4. 1 ring and 3 pi bonds. So benzene fits that formula. Could I come up with something else that fits the same formula? Sure. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. It helps if you have the right number of carbons. 6. 2 pi bonds plus 2 more pi bonds, 4 degrees of unsaturation. Yeah? Du. You need to be able to look at a molecule and know how many degrees of unsaturation it has. You need to be able to look at a formula and calculate the number of degrees of unsaturation. But this time we're focusing all on family 1, and that's all about alkenes and alkynes. Let's get started naming alkenes. So the parent chain is the longest chain with the most double bonds. Okay. Drop ane, add ene. Okay. If you have 2 double bonds, it's not an ane, it's an ene, but it's a diene, because you have to acknowledge both of them. Give the smallest number to the carbon-carbon double bond, unless a higher IUPAC priority group is present. So far to us, that means alcohols and amines. The number belongs to the first carbon in the alkene, because it needs to be numbered sequentially. Okay, we've already talked about E and Z, but we have not specified exactly how to name alkenes overall. So the nice thing about these alkenes that I've chosen to name, we're not worried about whether they're E or Z. We do know that. We will go through an example or two in a moment that have E and Z, but not these. So this chain has already been numbered. We're trying to find the longest chain that has the most multiple bonds. So that's 6 for this one. So that makes this a hexene, but you have to tell where the ene is, because 1 hexene is very different from 2 hexene, which is different from 3 hexene, and 4 hexene is not a thing. It means you numbered the wrong direction if you name it a 4 hexene, and that's your highest priority functional group. Okay, I digress. There's 3 carbons hanging off of carbon number 2. It's a 2 propyl 1 hexene. Okay, numbering the carbons here, 1, 2, 3, 4, 5, 6, 7. The reason I number that direction is an alkene is higher priority than halogens in naming of IUPAC rules. So that makes this a heptene. It's a 1 heptene. There's a bromo on carbon 5, a chloro on carbon 4. Alrighty. This chain numbers this direction because that gets my substituents the lowest number possible. When going that direction, my substituents are 2 and 4, versus if I numbered the other direction, my substituents would be 3 and 5. 2 and 4, 2 is a smaller number, so we're numbering it that way. It's a hexene. Where's the ene? On carbon 3. It's a 2-bromo, 4-methyl, 3-hexene. Okay. We've already seen this whole slide. We're not going to name all of these things, but we are going to specifically name this guy. This is a 4-carbon chain, so it's a bute, it's a butene, it's a 2-butene, it's a 2-fluoro. But that's not good enough. That's not the end of the name for this guy, because you need to specify, because this one is drawn out, you need to specify the absolute configuration around that double bond. Is it E? Is it Z? Is cis or trans acceptable here? Potentially, yes. In this specific example, yeah, it is. This is a Z double bond. Highest priority fluorine, highest priority methyl. They are on Z same side. Z, 2-fluoro, 2-butene. One little side note before we move along. That Z is often left without the number, but if you have multiple alkenes or multiple asymmetric carbons, you need to specify a number in front of the letter that you're giving. So sometimes people will say this is 2Z, 2-fluoro, 2-butene, but when there's only one asymmetric carbon, one stereocenter, it's understood when you give one letter where that is. Maybe that makes sense. I'm ready to move along. Let's name a big beast like this. So the first question is, what functional groups do we have? We have an alcohol, we have an alkene, and we have an amine. You knew that, right? Yeah. We have an alcohol, we have an amine, we have an alkene. This little brace over here is to say alkenes and alkynes have equal priority in the naming rules. So these guys are equal priority. Everything below that squiggle I just made is equal priority. And then amines and alcohols are up there. So Of our three functional groups, the alcohol is the highest priority, the highest IUPAC nomenclature priority. I think it's worth a little side note here to say, now that you've learned Kahn-Ingold-Prelog priority rules, you need to keep Kahn-Ingold-Prelog priorities separate from IUPAC nomenclature priorities. Isn't that fun? They are two separate systems with two separate purposes. IUPAC priorities and Kahn-Ingold-Prelog priorities are not the same thing. Okay, moving on. So the alcohol is my highest priority. That means the alcohol gets the lowest number possible. The lowest number that's going to be possible on this chain is 3. So this compound is a 3-ol, a 5-ene, a 6-amino. The reason it's called an amino is because when amines are not the highest priority group, it's named as a prefix instead of a suffix. So 6-amino. There's these things that need designation as well, and luckily they're the same. So that's an NN dimethyl. So the ol takes over the root name. Ene kind of goes in the middle, always and forever. And then amino is going to be a prefix. Dimethyl is a prefix. And my parent name is a hexane, or a hex. Okay, how do I assemble all of this? It's a hex, ene, 3-ol. You can call it a 5-hexene 3-ol, or a hex, 5-ene 3-ol. Just like the alcohols we named previously, you can squeeze the letters, the numbers in between the letters like these. Because you have an ene and an ol, and both of those change the parent name, the ol definitely has to be squeezed between the ene and the ol. These are your only two options. You cannot call it a 5-3 hexenol. The 3 has to be between the ene and the ol to specify that's where the ol is, and then the 5 can become between come between the x and the ene, or outside the hex and the ene. Whew. So that takes care of this thing, and this thing, and that thing. So what we have left is amino and dimethyl. So 6-amino comes first. NN dimethyl next because of alphabetization. I can't squeeze that in there very well. Yeah. But that's not all. Oh my god. Yeah, that's not all. Well, what's missing? The absolute configurations. We need to specify this asymmetric carbon, and is it R or is it S? And we need to specify this alkene, and is it E or is it Z? Oh, yeah. The alcohol is, pause, R. 3R is my alcohol, and the alkene is Z, 5Z. So really the beginning of that name is 3R, 5Z, in parentheses, dash, 6-amino, NN dimethyl, 5-hexene 3-ol. Yeah? It's a beast. I told you it was a beast. But that's the whole process of how it's named. Okay, so that was a beastly alkene. A beastly alkene-ol thing. What about cycloalkenes? It's the same as what we've done, except it's not an ane, it's an ene. If the highest priority group on your cyclo thing is an alkene, it is understood to have carbons numbers 1 and 2. If there is a higher priority group present, you must specify the number of the alkene. Let's see. The first couple already have numbers. So we have an ethyl substituent and an alkene. Alkenes are higher priorities than ethyls, so that's why the numbering goes this way to give me that name. Alkenes are higher priority than methyls, so alkene must get the lowest number possible, and I should have pointed out previously, the alkene must be numbered sequentially. You cannot say 1, 2, 3, 4, 5, 6. The alkene must be numbered sequentially, so that's why that one gets this name. And this one gets that name. The numbering of the chain in this next one is a little bit tricky. Alkene must be 1 and 2. So I could number it with the red numbers 1 and 2, or I could number it with the green, nope, that's blue, with the blue numbers 1 and 2. If using the blue numbers, alkene is on 1, chlorine is on 2, and chlorine is on 3. Okay, if numbering with the red numbers, alkene is on 1, chlorine is on 1, chlorine is on 6. Because it's a direct comparison, both blue and red have a substituent on number 1, but the red has a substituent on number 1, while the blue has it on 2. Blue is not the way to go, because 2 is a bigger number than 1. You number it according to the red numbers, and that's how you get 1,6-dichlorocyclohexene. Note, in all of these, I have not had to give the alkene a number because it's understood at carbon number 1 because I've been naming things that don't have higher priorities. I got one more that does not have a higher priority. 1, 2, 3, 4, 5. For similar reasons to the last one I just explained, the methyl there is beneficial for starting the numbering at that point. Alkene is higher priority than alkyl groups. So that's why that's my name. And in this last one, I have an alcohol. Alcohol is priority number 1. So this is a cyclohexene all. I almost put a dash there because it's my habit. But since it's named as an all, you know that all is on carbon number 1. So you must give the ene a number. We could name it 2-cyclohexenol or cyclohex-2-enol, like that. And there's one thing missing. It's an R. Got to specify around that alcohol whether it's R or S. 1 to 2 to 3. I should probably have changed my colors. Hydrogen, lowest priorities in the back. R. All right. We're going to continue our journey of naming so that I can get it out of the way. Alkynes are also unsaturated compounds. The way you name alkynes, so similar to naming alkenes. You don't add ene though, you add ine instead. If there's 2 of them, it's a diene. The longest chain, 1, 2, 3, 4, 5, 6, 7. It's a hept. It's a heptadiene. It's a 1,5-heptadiene. 1, 2, 3, 4, 5, 6. It's a hexine. It's a 2-hexine. It's a 4-methyl-2-hexine. Okay. What if you have alkenes and alkynes? The way the name is constructed, it's always called an ene-ine. It's never called an ine-ene. But you give the number to the... You give the smallest number to the multiple bond at the first point of difference, regardless of type. What I mean by that is when you have alkenes and alkynes, you find the longest chain that has the most multiple bonds, and you give those multiple bonds the lowest number possible, whether it's an alkene or an alkyne, but the name is always written as an ene-ine, never as an ine-ene. Let's do an example to see if that means anything to you. Here's some. So I have an alkyne and an alkene here, but I'm just aiming at finding the longest chain with the most multiple bonds and giving all the substituents the lowest number possible. So I'm going to have a 1 and a 4 substituent if I number it this way. So it's a hex. It's a hexene-ine. It's a 4-hexene 1-ine. Oh. You could also name it a hex 4-ene 1-ine. It's all up to you as to whether you squiz the number between there or not. The ine number is going to have to be squizzed between there because you have to give numbers for the ene and the ine, and only one can go out front. Same with the alcohol we did a minute ago. This is the same compound, except the enes and ines are reversed. You name it the same thing, except give the lower number to the ene because it was at the end of the line. Same compound, just different alkenes and alkynes swapped. You do not prioritize one ene over another ine or vice versa. In this last one, we have multiple alkenes. We're trying to give them the lowest number possible, and that's numbering this direction. So that's a hept. It's a heptadiene because we have an ene on carbon 1 and carbon 3. And we have an ine on carbon 5. Okay. We have this group as well. That group is 2 carbons, so it's an F. It would be an ethene if you named it individually. But it's not an ene, it's an ethenol, YL, to tell me that it's hanging off of the main parent chain. So it's a 3-ethenol. 1,3-heptadiene,5-ine. That's a mouthful, right? There's one other thing I want to say about this group down here. The common name of that group down there is vinyl. You ever heard of vinyl in like industrial things? Vinyl flooring is one way. Vinyl flooring is often vinyl chloride, like that has been polymerized to make polyvinyl chloride. Polyvinyl chloride is known as PVC. So the same thing that's vinyl flooring also is PVC piping for your plumbing pipes. Also, IV bags are made out of polyvinyl chloride. It's a polymer that has a lot of industrial uses. So vinyl is the common name, but that vinyl, especially vinyl chloride and other similar things, vinyl is still very prevalent in a lot of industrial terminology, but IUPAC would say name it this way as an ethenol. Okay. That's enough naming. I've had all I can take anyway. Let's talk about other properties of alkenes. To do that, we will revisit molecular orbital theory. Molecular orbital theory is something you learned about in general chemistry. Maybe you don't remember much, but we'll visit a little bit. Molecular orbital theory talks about HOMOs, which is highest occupied molecular orbital, and LUMOS stands for lowest unoccupied. As in, has electrons in it, doesn't have electrons in it. Highest occupied, has electrons. Lowest unoccupied, has no electrons. Molecular orbitals are descriptions of where electrons reside within a molecule, hence the word molecular orbitals. Within a molecule, there's a lot of electrons. The places they reside are called molecular orbitals. So, there's a highest occupied, lowest unoccupied within all molecules. There's an energy gap between those that's important for what we're about to say. If you shine some light or some energy is transferred somehow, and we're saying it's light energy here, if you shine some light energy onto a molecule, some of the electrons get promoted to higher energy molecular orbitals. So here's the promotion after the light energy has been absorbed. When the electrons are promoted to higher orbitals, that's called an excited state. Things don't exist in an excited state for very long, so they relax back down, and when it relaxes back down, often a photon is emitted. You remember talking about photons? So when a photon is emitted, that photon will have different wavelengths, and sometimes the photons that are emitted are wavelengths of light that are in the colored spectrum. That was really confusing. I know, it's okay, bear with me. The energy gap is what we're mostly concerned with. The energy gap determines the wavelength of light needed to excite electrons from the HOMO to the LUMO. The energy gap for ethylene requires a wavelength of 171 nanometers to excite an electron from here to there. Okay. The wavelength of light needed to excite an electron in butadiene is 217 nanometers. The wavelength of light needed to excite an electron in hexatriene is 268 nanometers. Okay, get to the point. Well, ethylene has 1 pi bond. Butadiene has 2 pi bonds. 135 hexatriene, 3 pi bonds. As you got more pi bonds, the energy gap got smaller, And the lambda max, that's what this is down here, the lambda max got bigger. Remember, energy and wavelength are inversely proportional? Oh, let's throw it way back. So, these molecules down here, this one not included, these molecules here are conjugated. What does it mean to be conjugated? Single, double, single, double, single, double. That's one way to say it. Double, single, double, single, double. Yeah. Benzene is a conjugated molecule. So we're looking for conjugated molecules because conjugated molecules, or molecules with pi bonds period, but conjugated especially, absorb light in the UV and visible region. Okay, here's 2-methyl-1,3-butadiene, that's that molecule. The lambda max for that molecule is 224 nanometers. UV visible spectroscopy measures the lambda max. It measures the wavelength of light needed to promote electrons from the HOMO to the LUMO in any given compound. Well, UV spectroscopy is used to measure those lambda max values. What can you deduce from lambda max values? The more highly conjugated a system is, the longer the lambda max is going to be. So eventually, if the lambda max gets long enough, that means that you will have a lambda max, that means you could have, a lambda max between about 400 and 700 nanometers. And if you absorb light 400 to 700 nanometers, you will appear as a colored compound. And so colored compounds are known as chromophores. So we'll look for these kinds of things to help us determine if a system is conjugated. Things that are conjugated might be colored. Butadiene has 2 conjugated double bonds. Its lambda max 217. That's not between 400 and 700. It's colorless. Beta carotene, you hear that? Carotene has 11 conjugated double bonds. Its lambda max is in the visible spectrum. This is an orange compound, carotene. It's an orange compound. It's the reason carrots are orange. It's also the reason flamingo feathers are pink, a slight variation of this compound. Check it out. You have maybe done a titration before in your life and used phenolphthalein in that titration. This compound on the left is a colorless compound because there's not sufficient enough conjugation in it. The compound on the right does have enough conjugation to appear colored. It's pink, in fact. So if I look at the colorless compound, this carbon is sp3. sp3 carbons cannot be part of a pi system because they are involved in no pi bonds. So what that means is, although this ring is conjugated, this ring is conjugated, and this ring is conjugated, there's no communication between each other because of that sp3 carbon in the middle. But in the molecule on the right, there is conjugation throughout the whole molecule, because every single atom in that molecule is sp2 hybridized. There can be communication, meaning I could draw resonance arrows that flip electrons throughout this whole molecule. And anytime you can draw resonance arrows, they'll show up eventually. Anytime you can draw resonance arrows like all of those, that whole system is conjugated. And when that whole system is conjugated, it's likely to be a colored compound because it probably has a lambda max in the visible region. I realize that was pretty confusing, but I'm done.